guys, welcome back to A Case of Econ Struggles. Today I'm going to talk about the two-period consumption problem. This is a problem that I've been seeing a lot of people ask about lately, so I'm going to go ahead and do a video about it. In this video specifically, what I want to do is I want to talk about how to better understand the two-period utility maximization problem. Now in this problem specifically, I'm going to use an endowment rather than a labor-leisure decision on top of the two-period consumption decision, but if that's something that people are interested in, go ahead and put that in the comment section below, and I can do a version of this where people also have the decision of how much to work or not. But for this problem, I'm just going to extract away from that. One of the main things that I want you to be able to understand after watching this video is how to write the present value of the lifetime budget constraint. And then I want you to be able to solve the intertemporal utility maximization problem. I'm going to do this without prices, and then at the end, I'm going to show you that whether or not we add in prices, whether or not those prices change, whether or not we have inflation, doesn't fundamentally change the answer to this problem. So let's go ahead and get right into it. Timestamps are below if you would like to jump around. So here's the setup for this two-period utility maximization problem. We're going to have Bill. Bill's going to live for 2 periods, and each period, period 1 and period 2, he's going to get some coconuts for free that arrive on his doorstep. We're going to call those as endowments. Now from period 1 to 2, Bill can either loan or borrow some coconuts, but he's going to get some interest or have to repay some interest in the next period. We're going to call that interest rate R, and we're going to say that Bill has a utility function over consumption today and tomorrow, and it's going to be some utility function. I'll fill that in when we get there. Just for some notation, I'm going to call period 1 or today period T, and tomorrow I'm going to call that T plus 1. Now I said he's got endowments in each period, so I'm going to call those ET and ET plus 1. The number of coconuts that Bill consumes in each period, that's going to be CT and CT plus 1. How much Bill chooses to save or borrow from period T to period T plus 1. I'm going to call that ST, because ST plus 1, how much Bill would choose to borrow or save in period 2 into period 3, is 0 because Bill isn't going to be around for 3 periods, so there's no point in him borrowing or saving from period 2 into period 3. And again, I'm going to ignore prices for now. This is going to be solely in terms of coconuts. We'll add in prices at the very end just to show that prices don't fundamentally change the answer to this problem. Just to show a graphical depiction of what's happening, what we've got is we can start in period T or period today. And if I start in period today, what you're going to see is that Bill is going to get an endowment, a certain number of coconuts, or he's going to show up on his doorstep. From those coconuts, Bill's going to choose how many coconuts to eat or consume. That's going to be CT. And he's also going to choose how many coconuts to borrow or save between period T and period T plus 1. And so in this picture, I've shown Bill as sort of a lender, so he's lending these coconuts out to other people. But of course, it could be negative. He could be borrowing coconuts from someone else. He's got to repay those in the next period. But in this example, if he's going to lend out some coconuts in period T, the amount of coconuts that he gets repaid tomorrow is going to be 1 plus the interest rate times the number of coconuts that he lended from period T into period T plus 1. He's going to have an additional endowment that he gets in period T plus 1, and because Bill is not going to be around for a third period, he's going to take all the coconuts that he gets from being repaid and all the coconuts that show up on his doorstep, and he's going to consume all of those coconuts. And so sort of the ultimate question we're trying to answer in this problem is, what is the optimal amount of consumption today and consumption tomorrow? How much should Bill save versus consume today in order to consume a certain amount tomorrow based on his endowment, the interest rate, and all those sorts of things. So in order to solve that question, we first got to really quickly brush up on present value, because we have coconuts in 2 different periods, and we know from basic economics that coconuts today are not exactly equal to coconuts tomorrow because of this interest rate. We know that coconuts today are worth a certain amount of coconuts tomorrow, discounted back 1 period using the interest rate, 1 plus R. I've got a video that shows exactly how this present value versus future value stuff kind of works. I'll put that in the top right hand corner right about now in case you want to check it out, and I'll also put a link to it in the description. So if we know that coconuts today are not worth the same as coconuts tomorrow, well, we need to think about, well, what is Bill's lifetime present value, both of his income and the amount that he's going to spend? And so we need to think about Bill's intertemporal budget constraint, or the present value of his lifetime budget constraint. And so what we're going to do is we're going to start with period T, that's period today, and in period today, in period T, Bill's endowed with some coconuts, and we said that he's going to split them between consuming and saving. So he gets CT plus ST, and again, a budget constraint is money coming in, has to be equal to money spent. Okay, so that's period T. In period T plus 1, he's going to get his endowment, plus 1 plus r times st, whether or not that's a negative value because he borrowed in period t and has to repay in period t plus 1, or it's a positive amount of coconuts because in period t he lent someone else some coconuts, and so now in period t plus 1 they're paying it back. And that's going to be equal to ct plus 1 because we said that he's going to spend all the coconuts he has in period t plus 1 because he's not around for period t plus 2. Now, in order to take that into the same units, or to make those coconuts comparable to coconuts in period t, we're going to present value, we're going to discount those coconuts in period t plus 1 back to make sure they're comparable to coconuts in period t. And we do that by taking this and multiplying everything by 1 over 1 plus r. Now, when we do that, what you're going to see is the savings is going to cancel because this is going to be 1 plus r st times 1 over 1 plus r, which is just st. And that's going to be on the left-hand side of this equation, whereas in period t, that same st was on the right-hand side of the equation. And this is important because savings are not earning Bill any money. He's not benefiting in one way or another from borrowing or lending coconuts, other than the fact that that mechanism is allowing Bill to transfer coconuts between today and tomorrow. So you would expect when we did a present value of this lifetime budget, that savings would not enter into here because at the end of the day, Bill gets some coconuts on his front porch and he eats some coconuts, and fundamentally those two values should be equal to each other no matter in which period Bill chooses to eat a certain amount of coconuts. So real quick, just to give a graphical description, I'm going to take this budget constraint and I'm going to make a graph where I have the amount of coconuts that Bill consumes in t plus 1 on the y-axis, the amount of coconuts that Bill consumes in period t on the x-axis, and I'm going to rewrite this budget constraint so that it's ct plus 1 equals something. When I rewrite that equation, I get 1 plus r times this whole thing minus 1 plus r times ct. And so when I draw that line, what's going to happen is suppose that this is the amount of coconuts that Bill's endowed with in period t plus 1, and this is the amount of coconuts that Bill's endowed with in period t. Now, if Bill did not do any borrowing or lending, this is exactly the amount of coconuts that he would eat. He would basically wake up on day t, he would eat the amount of coconuts in the box if he wasn't able to save or borrow, and then he would wake up in period t plus 1 with a new certain amount of coconuts, et plus 1, and that's the amount of coconuts that he would eat in period t plus 1. Now, what we just said is that this sort of borrowing lending business allows Bill to trade off between consuming coconuts in period t and period t plus 1. So let's take it to the extreme. Let's say that Bill decides to eat 0 coconuts in period t, and Bill chooses to save or lend all of those coconuts to someone else. Well, then what he's going to be able to eat in period t plus 1 is he's definitely going to be able to eat the amount of coconuts that showed up in the box on his porch in period t plus 1. And then he's going to get all of the ET that he lent out in period t, all the coconuts that showed up in period t that he lent to someone else, plus the interest that that other person is going to have to repay Bill in order for the fact that Bill lent him coconuts in period t. And so this is the maximum amount that Bill can eat in period t plus 1, given that he doesn't eat anything in period t. On the other hand, if Bill does not want to eat anything in period t plus 1, what is the maximum amount that he can consume in period t? Well, he can definitely consume all the coconuts that showed up on his doorstep in period t. Doesn't have to borrow or lend against coconuts that exist today. In order to borrow against the amount of coconuts that he's going to receive in period t plus 1, however, he's got to make sure he's aware of the fact that he's got to repay that with interest. So he's going to go et plus 1 divided by 1 plus r to make sure that when he gets those coconuts in period t plus 1, he has just enough to repay the person who lent him coconuts in period t. He's able to perfectly repay them in period t plus 1, but he's not able to eat anything in t plus 1 because he gave away all his coconuts, all his down coconuts, in order to repay that loan. That's sort of what's happening with the budget constraint. Now, the slope of this budget constraint, then, is negative 1 plus r, because Bill is trading off a coconut today. If he gives up a coconut today, he doesn't get 1 coconut tomorrow. He gets 1 plus r coconuts tomorrow because of that interest rate, and that's going to be important. So now with this budget constraint, you can sort of almost imagine, even though I haven't drawn it, some sort of indifference curve going through here, and we're just going to find the tangency point between this indifference curve and this budget constraint. That's going to tell us the optimal amount for Bill in terms of consumption today and consumption tomorrow. Now, when I introduce this utility function, I could be sort of vague and talk about, well, it's got a utility. We're going to have marginal utilities of consumption today and consumption tomorrow. And I think that would be kind of too vague. So what I'm going to do is I'm just going to give you an example utility function. So maybe your example utility function is just CT times CT plus 1, or maybe it's the natural log of consumption today plus the natural log of consumption tomorrow. Both of these utility functions give you the same result, and if you don't believe me, try it after this video and see if you get the same result, and if you do, let me know in the comments below. So what we're going to do is we're going to go back to our main utility maximization problem, where unsurprisingly we're going to have this idea that at the optimal, the marginal benefit is equal to the marginal cost, both in terms of consumption today and consumption tomorrow. So if I think about the marginal utility of consumption today, if I use this utility function, that's just coconuts tomorrow, or CT plus 1. Now what is the price I pay in terms of giving up a coconut today? Well, I don't have prices. Instead, what I'm saying is when I give up that coconut today, I get a coconut tomorrow. So the price of giving up a coconut is actually 1 plus R. Now, in terms of CT plus 1, the marginal utility is just CT, and the cost of giving up a coconut tomorrow is just going to be 1. And so that's the amount of coconuts that I give up. Okay, so from this, I get that CT plus 1 equals 1 plus R times CT. And then what I can do is I can combine that with the intertemporal budget constraint, or the lifetime budget constraint present value that we talked about earlier. So I'm just going to make that substitution of CT plus 1. And when I do that, I get that CT, the optimal amount of consumption today, is 1/2 times ET plus 1 over 1 plus R. And this guy, this is just the present value of our lifetime income. And so what this is saying is, how much should I eat today? Well, I should eat half of the present value of my lifetime income, and I should save the other half for tomorrow. Now, this really came about because of the fact that in my utility function, I had sort of equal coefficients on CT or CT plus 1, or sort of that I had just ones in front of the natural logs, right? So I care about both today and tomorrow equally. I want a consumption smooth. If you haven't talked about consumption smoothing, don't worry about it. If you're curious, I've got a video on consumption smoothing. Put a link to it in the description below, and it'll pop up in the right hand corner if you'd like to check it out later. But again, we're just saying that I'm going to consume half the amount of my lifetime income today and save the other half for later. Now, I said at the start of the video that I would come back and show you that prices don't matter necessarily for the overall answer to this question. By the overall answer, I just mean based on the utility function, we want to spend half of the present value of lifetime income today and save the other half for tomorrow. So just to show you that prices don't actually matter, suppose we have prices. Suppose the price of the coconut in period T is PT, and suppose that the price of the coconut tomorrow is PT plus 1. I can rewrite the period T budget constraint using savings, and I can also rewrite the T plus 1 budget constraint, again, sort of using these prices. Now, where it gets tricky is when I think about the PT savings. Okay, well, I got 1 plus R, but now I need to divide it by PT plus 1. So what this is saying is, suppose that the price was 1, and I chose to save 2 coconuts. Okay, so I've got $2 worth of savings. So those $2 get multiplied by 1 plus R, and this is in dollars. Okay, if I want this to go back into coconuts, then I need to divide it by basically the price in period T plus 1 to account for inflation. And that's going to be PT plus 1 times CT plus 1. So now my lifetime income is just the prices, and for the prices of and down in period T plus 1, it's ET plus 1 over 1 plus R, and basically accounting for inflation. That's going to be the same thing for consumption. Now what I'm going to do for the utility function is exactly the same thing in terms of marginal benefits and marginal costs. But now if I give up a coconut today, well, the marginal benefit of eating a coconut today is based on how many coconuts I eat tomorrow. The price that I give up for eating a coconut today is I get 1 plus R in terms of tomorrow, but I also have to address the fact that there could be inflation. So by waiting, this inflation might erode the value of that coconut, so that's a cost that I got to be aware of. In terms of giving up a CT plus 1, that's going to be PT. So now I can just say that CT plus 1 is 1 over plus R over 1 plus pi times PT times CT. Why am I saying 1 plus pi here? Well, 1 plus pi, if I think about inflation, inflation is just price tomorrow minus price today over price today. And I'm just going to add 1 to that. And so when I take this 1 and I want to add it to something with PT in the denominator, I make both the numerator and the denominator PT, and I get PT plus 1 over PT. Now what I'm going to do is I'm going to go back to that budget constraint. First, what I'm going to do is I'm going to take this lifetime budget constraint and I'm going to rewrite it with the pt plus 1 over pt being 1 plus pi. So I'll go ahead and say that this guy right here becomes the 1 plus pi, and this guy right here also becomes 1 plus pi. And then what I'm going to do is then I am going to substitute ct plus 1 is this business in there. And what you're going to see is that this 1 plus r over 1 plus pi is going to cancel with the 1 plus pi over 1 plus r. That's going to be a ct right there. And so what you're going to get is you're going to get, if I solve for ct star, it's going to be 1/2 times 1 over pt, pt et plus 1 pi over 1 plus r et plus 1, which is again just 1/2 of the present value of the lifetime income, just now accounting for prices. So again, even though prices made the math more complicated, it didn't change the ultimate answer that we're going to consumption smooth, and I want to eat the optimal consumption for me in period t is just 1/2 of the present value of my lifetime income. So again, there's a lot of ways we can go with this. We can talk about how we can use this to build macro models. We can talk about what happens when Bill decides whether or not to work on top of this optimal consumption decision. So instead of getting endowments, he's got to choose how many hours to work for a wage, and that's going to decide how much he gets. As you might imagine, what's going to happen? How much should he consume? It's still going to be 1/2 of the present value of his lifetime income, but now his income is going to depend on how much he works rather than just having coconuts show up on the door for free. So again, if you've got any questions, if this was helpful, please let me know in the comment section below. If you haven't already, please like and subscribe. We'll see you next time for another case of Econ struggles.